Hi there. I really like the DPS series of adjustable power supplies because they provide a very affordable and effortless way of making a bench power supply for your lab. If you have seen some of my other videos, you will have noticed this power supply. It features a DPS-3005 which can provide 30 volts at 5 amps, adjustable to 10 millivolt and 1 milliamp. The modules are available with communications or without, and when I bought this module more than a year ago, I picked the module without the communication capability. Now I'm aware that there are ways of replacing the firmware with an open source version called OpenDPS and probably add communication as well. When I recently saw a discounted DPS5005 with communication on Banggood, I thought I'd get it to explore the comms part with an eye to possibly change the firmware as well. However, in this video I'm only looking at the DPS5005 with the original firmware. The unit arrived in this little box here. Complete with two auxiliary boards and a cable. One board is a USB interface, while the other one is a Bluetooth interface. With the provided cable you can hook up either one to the power module, but not both simultaneously. There are plenty of videos and reviews of the DPS modules out there, so I'm not going to add another one. Briefly, this here is where you plug the cable in for the comms module. Other than that, you provide up to 50 volts DC inputs here, and this is the output with the voltage and current selected on the DPS unit. The big chip on the USB board is a CH340G, which provides a USB to RS-232 conversion and supports speeds from 2400 to 115,200 bits per second. It's common to a lot of Arduino clones to provide the USB to serial conversion with this chip. It was immediately recognized under Linux, but under Windows 7 I had to first download and install a driver for it. What I really like is that the board includes two EL357N optocouplers on the upper left here, and for the electrical safety it is worth looking at this a bit more detailed. So I reverse engineered the board around the two optocouplers and the connector to the DPS. On the right side here is the connector to the DPS module with the labels as on the PCB and the colors of the provided cable. Somewhat confusingly, the labels refer to the USB side of the world, so R pin is connected to the DPS transmit and the T pin is connected to the DPS receive. To send data, the DPS pulls the R pin to ground, which will light up the LED inside the optocoupler. This is then detected by the built-in phototransistor and amplified by an external transistor before going to the RX pin of the CH340 chip. For transmission from the USB to the DPS, the circuit is simply reversed using the second optocoupler. Now the CH340 transmit pin pulls the LED to the ground if needed, which is then detected by the phototransistor on the DPS side, and an external transistor powered by the DPS boosts the signal further. You can see that the DPS side and the rest of the board are completely isolated from each other. This is important because otherwise the output of the DPS5005 would always be referenced through the USB cable and your laptop or PC to ground, which is not something you want for a lab power supply. Of course, to achieve this, the input power to the DPS module itself must not be ground referenced already. Let's have a look at the Bluetooth board. It is essentially one chip, the BK3231. The BK3231 is essentially an ARM9 based microcontroller with an added Bluetooth interface. Bluetooth version 3.0 and ARM9 both indicate that this is a fairly old chip. It still has a reasonable amount of onboard flash and RAM memory, lots of digital I/O and even a 10-bit ADC. It certainly has enough processing power to run firmware which could translate the serial protocol from the DPS into something completely different on Bluetooth. Speaking about protocols, I think it's great that not only did the Chinese manufacturers of the DPS use the well-documented Modbus standard for their serial protocol, they even provide detailed message documentation and examples. I'll add the link where you can download that information and user guides into the description of this video. The module implements 3 Modbus messages: read holding register, function code 3, write single register, function code 6, and write multiple registers, function code 16 or hex 10. Each Modbus message needs to start with a period of silence to allow systems to recognize that any previous message is definitely finished. This period of silence is usually treated as 3.5 times the period to transmit 1 byte. This silence is then followed by the first byte containing the slave address, followed by a function code, the data payload, and the 16-bit checksum. If you hold the V up button during power up, the DPS presents a screen to change its Modbus slave address and the communication speed, as well as the Bluetooth pairing code. The maximum speed is just 19,200 bits per second, which at 10 bits per character translates to 1920 bytes per second. I tested it and it worked at that speed on both USB and Bluetooth, but if you are using the available Android app, you are probably stuck with the default of 9600 bits per second, because I did not see a way of changing the speed in the app. However, even with the 19,200 bits per second, the comms throughput isn't all that exciting. So if we take a look at a timeline, the big black arrow, you see 2 Modbus messages following each other as close as theoretically possible. Each message is preceded by its 3.5 character worth of silence. Since some of the messages are quite short, 8 bytes for example, the added silence adds almost 50% to the time needed for transmission, reducing the throughput. In reality, however, the situation is actually worse. After sending a message to the slave decodes it, verifies the checksum, and then puts together a response. All that takes processing time. Then the response is put on the bus, preceded by the usual silence. I found that the DPS module did not respond to any further messages until the response for the first message was out. This effectively reduces the throughput to a half duplex operation. The only good thing is that as long as you talk to only one slave, the half duplex operation slows repeated transmissions by the master so much that you don't have to add silence periods. There's already plenty of silence between messages on the bus. So far, everything I said applies to serial connections using the USB interface, and my software was working nicely through that. But then I tried the Bluetooth module and got lots of checksum and message errors with the occasional good message exchange. On closer investigation, it turns out that in this case, the communication through Bluetooth uses a protocol called RFCOM, which emulates a serial interface. That in turn relies on the packet-based Logical Link Control and Adaptation Layer Protocol, or L2CAP, to get data across. Without deep diving into the Bluetooth protocol stack, it seems that at least the implementation in the provided Bluetooth module packs the serial data it gets from the DPS module into data packets and then sends them out. This not only strips the silence part, but it also breaks messages. If a packet has no more room for the complete message or needs to be passed to the radio before all bytes from the DPS module have been put in, these bytes are not lost, they are just simply put into the next packet. Unfortunately, on the receiving side, you end up with an unexpected gap. This looks exactly like the silence period used in Modbus to separate messages, and therefore my program decided the first part was the full message, which was obviously incomplete and failed the checksum validation. The remaining bytes were then seen as the start of a new message, which made again no sense. The only way to make my program work is to change it to assemble complete messages from fragments received. Luckily, since we are still half duplex, the send function in my program knows exactly what length of response is to expect from a DPS module and can tell this to the read function, which therefore no longer needs to rely on silence periods to find the end of a message and the start of the next one. This is a simple test program to read the set voltage and current and the actual output voltage, current and power from the DPS module. It uses the serial communication and works through USB or Bluetooth on Linux or Windows 7. I have not tested it on other machines. It is pretty straightforward. We open the serial port here. Some definitions about registers straight out of the DPS manual. The function to calculate the checksum. And two functions to send a read holding register command and another one to send a write register command. In both cases, the functions then proceed to read the response from the module before returning. Note that the functions pass the expected length of the return message in bytes to the read response function. As discussed, this is needed because the Bluetooth may break messages into separate chunks. The read response function reads bytes from the serial ports and assembles them into messages contained in the variable buff. If the checksum is correct, this function prints the content of the two expected messages. Last not least, you can see the program runs in a loop where we read and print the actual output values and at the same time increment the output voltage in steps of 0.1 volts until 5 volt is reached and the output voltage is set back to 0. Here you can see the program running. The set voltage increments as expected in the top line of the DPS display, while the output follows with a little delay. The right screen shows the printout of the program, showing results from the polling of the output values and the responses from setting the voltage. This test program has no delays and runs at 19,200 bits per second, as fast as the DPS module responds. It shows the maximum speed that can be achieved in talking to the DPS module, which is about half a second. So what about the available software? You have a choice of Windows or Android. On the left you see the basic and advanced screens of the Windows version. On the right is the image of the Android version from the Google App Store. The Windows version only works from Windows 7 and above, and the Windows version can use USB or Bluetooth to connect to the DPS module, while Android uses only Bluetooth. You can see that the basic screen of the Windows version as well as the Android app basically offer the remote control of all functions you can do from the front panel of the module as well. So in my opinion, that part is not much value added. The graphical plots may be useful for some, although I prefer to record the data and do my plots and additional calculations later. The Android version allows recording. Some version of the Windows software have that too, but apparently not all of them. The advanced screen of the Windows version is more interesting. The auto test allows up to 10 steps of voltage and current settings with a selectable delay between each step. Then there are the voltage scan and current scan options, which allow setting a start, stop and step value and a delay for each step. These automations could be quite useful, but I find them too limiting for my purposes. Moreover, I try to avoid Windows, so I did not investigate the Windows software any further, but I can say that the manual and screenshots of the installation manuals look really good, and I think a lot of effort was spent in making this a professional looking product. Before we move on, have a good look at the Android screen from the manual and remember that big orange circle to set values. I do have an old Nexus tablet, so I thought I'd give the Android version a quick test, which you can download as a DPS app from the Google Play Store. It comes with the usual advertising screen. It turns out that the software struggles a bit with the tablet display format, but essentially everything is there somewhere. More problematic is the absence of the big orange circle that one has to twirl to set values. Only a white box is displayed. In case you wonder, I had already paired the DPS module. Turning the output off and on. Changing the brightness works, and so does setting the voltage even though the circle is invisible. I tested the other functions, and apart from the absence of the circle, everything works fine, but I'm no fan of setting voltages live with a touch interface. It's very easy to accidentally overshoot and kill whatever is connected. So using the Android app is out for me, and besides being stuck on Windows, I think the provided control software isn't up to what I want to do. Remotely controlling the power to some device under test is just part of an overall picture. To begin with, the executed program needs to be more than 10 steps or a simple ramp, and it needs to be logging the commanded voltage and current and the actual data. Then I want to include other sensors, such as a camera or a multimeter. But rather than running these in parallel and having to manually sync their recording with the DPS5005, I want ideally to include their data at the right place into the recording, or at least mark it up in a way that helps me correlating the different recordings. I looked at available solutions such as LabVIEW, MyOpenLab, MATLAB, Simulink, and so on, and while some of them are free, they all seem to be too ambitious for my purpose, and a lot of effort has been spent on graphical interfaces, virtual front panels, and graphical programming languages, all of which I'm happy to live without. In the end, I decided to expand the little test program you saw earlier and create my own programming language, which is a fun project in itself. There are only 9 instructions, so bear with me when I briefly explain them. The first and possibly most frequently used instruction is set, which allows setting a new target value for the output voltage or current. The V or C specify whether the set command is for voltage or current. The same method, by the way, is used for all the other instructions. You can see the usage example here. The code in general is not case sensitive, so you can use uppercase, lowercase as you feel it. Each line contains only one instruction, and any parameter like the 2 for set are separated by spaces or tabs, not commas. Comments start after the hash character. It is worth noting that the program can't check if the set values are actually achievable with your hardware. There could be many limitations, from the input voltage and current to the DPS module to the characteristics of the device under test. For example, if it represents a high resistance, it may never draw 2.3 amps. Or if it has a very low resistance, the DPS may switch to constant current mode at 2.3 amps and reduce the voltage so far that it's less than 10 volts. A close relative to set is the INC, short for increment instruction, which applies a positive or negative delta to the voltage or current already set earlier. It makes creating ramps very easy. In this example, the set voltage was 1 volt, which is then incremented by 4.5 to get 5.5 volts, and then reduced to 5 volts by another INC instruction, which actually is then a decrement instruction, by using a negative value of 0.5. The program won't let you create negative voltages or current. In such cases, the value is simply set to 0. A very simple instruction is output, which simply turns the output of the DPS module on or off. The max instruction provides an easy way of setting the over voltage, over current, and over power protection values in the DPS module. The max values act kind of like a resettable fuse. If the voltage, current, or power exceed the set max values, the DPS module immediately turns the output power off. I must admit that because setting these protection values from the DPS front panel is so convoluted, I never bothered with it in my other DPS, but now I'm beginning to like the feature a lot. Max not only has the familiar V and C parameter, but also P for power. Note that the program checks if the protection has triggered, and it will stop execution since it doesn't make sense to continue. You must use the DPS front panel to set the voltage or current back to safe values to clear the protection status before you can try running DPS control again. Now it gets a bit more sophisticated. The if instruction sets a condition for either voltage, current, or power, as defined by the first parameter, V, C or P. The second parameter is the condition, which can be less or equal, greater or equal, or greater. The third parameter is the value to compare with. By itself, the if instruction only sets an active condition and continues with the next instruction. Conditions are only tested by the wait and goto instructions, and both of these instructions always clear the condition afterwards. Don't worry, this will become clearer when we discuss those instructions. There is only one active condition, so if you have two ifs following each other, the last one overrides the condition of the first one. There's one more note to add to the if instruction. Let's say you have this if here, which sets a condition for greater or equal 4.9 volts. Sometimes the DPS module may not quite get there, and it may display 4.89 volts instead. At least in my DPS I noticed that it can be out by a digit, usually underreading, that is showing a slightly lower value than the set value. If it is important to detect 4.9 volts reliably, it is better to test for greater or equal 4.89 or even 4.88. Whether you need this adjustment depends on how your DPS module behaves. The wait instruction normally delays execution for the number of seconds specified. However, if there is an active condition set by an if, the wait becomes conditional and delays until the condition is true. In this case, if the wait time was 0, it will wait indefinite, but if a non-zero time was specified, it acts like a timeout, that is, the wait finishes even if the condition was not true when the time has expired. This example here shows how to use if and wait instructions to make the DPS act as a constant current charger for a 12-volt lead-acid battery. I'm not recommending doing this unattended, and you should probably set the max values for protection as well. I have not tried this with a real battery, and I would definitely add a diode between the battery and the DPS to prevent the battery backfeeding the DPS output, which could damage both. We set the voltage to 14.5 volts, which should be the voltage when the battery is fully charged. The current limit is set to 2 amps and the output turned on. The next instruction is an if that sets a condition to test that the current exceeds 10 milliamps. Remember that if only sets conditions but doesn't test them. That job is done by the following wait instruction. Since its time parameter is 0, the wait is potentially indefinite. Why would you do something like this? It is really rather convenient, because this effectively stops a program until a device, in this case a battery, is physically connected. As soon as a current flow is detected, the wait finishes and the program automatically resumes execution. Since waits and gotos always delete conditions, the next wait is unconditional and simply delays for 5 seconds to let everything settle. The next if sets a condition whether the fully charged voltage has been reached. For reasons discussed earlier, this condition uses a slightly lower value in case the DPS module underreads the voltage. The next wait is therefore again conditional and keeps testing the condition set by the if. However, in this case we also have set a timeout value of 10 hours or 36,000 seconds. This means the wait will finish either because the battery voltage has increased to 14.48 volts or above, or after 10 hours, whichever happens first. The last step is of course to turn the output off to stop charging the battery. The goto instruction normally jumps unconditional to the instruction with a matching label. However, if there is an active condition set, the goto becomes conditional and jumps only to the label if the condition is true. If not, flows just continues with the instruction following the goto. As with wait, after a goto, the condition is always cleared and no longer active. This little example creates an upward ramp moving from 1 volt to 5 volts in 0.5 volt steps, with each step taking 5 seconds, then stays at 5 volts for 60 seconds, followed by a downward ramp in 1 volt steps, with each step taking 1 second. You can see how target labels are declared here, up and down. They have to be the first thing in a line. and end with a colon and be followed by an instruction. The colon is only there to distinguish a label from an instruction. It is not part of the label. For that reason, labels behind the goto have no colon. We start with the first increment by half a volt, which is followed by a normal wait instruction. Then the if condition is set up to test if we are still below 5 volts. The goto that follows tests the active condition, and if it's true, jumps to do some more incrementing. But if it's false, simply proceeds to the next instruction, which in this case is the 60-second wait. The downward ramp is programmed exactly the same way. We decrement by 1 volt, wait a second, then set a condition to see if we are still above 1 volt. The goto tests that, and if true, jumps to do some more decrementing. When the condition is finally no longer true, we have reached 0 volts and turn the output off just in case. If we would replace the output instruction with another goto up, it would be unconditional, since the previous goto had removed the condition, and we would have created an endless program producing an endless succession of up down ramps until we stop the program manually by hitting Ctrl+C on the keyboard. The record instruction sets the level of recording. Recording uses the comma-separated value CSV format that can be directly opened in Excel or other spreadsheet programs. Level 0 means no recording. Level 1 records only every time an instruction is executed that changes things, such as set or ink. This saves a lot of space if programs runs for hours, but you would miss any changes in current or voltage caused by the device under test. Level 2 includes level 1 and records regularly at frequency in seconds specified by the second parameter. But you can't record faster than about once every half second. With this mode, you would catch changes caused by the device, but only if they last long enough to be picked up by the next scheduled recording. Level 3 is my preferred mode. It checks voltage, current and power at the maximum speed of every half second, but only records if it detects that values have changed since the last recorded value. This provides the best way of not missing changes caused by the device under test, and at the same time it avoids recording endless successions of values that have not changed. The recording file name is created using the prefix rec followed by the digits that make the current date and time, and has the extension CSV. This ensures that the file name is always unique and multiple runs don't override each other's recording. The last instruction, call, is my way of expanding the functionality to control other things, such as additional multimeters or taking pictures. The first parameter must be a command that is understood by your operating system, for example Windows. The second and third parameters can be used for additional parameters for the command. In the following example, I show how the same command could be coded for Windows and Linux operating systems. Of course, you can use your own programs. For example, you may use a different program to take photos from a webcam. I selected FFmpeg because it's free and available for both Windows and Linux. The first set of calls invoke a script or batch file. The idea here is that this script or batch file somehow obtains a measurement value from a multimeter and prints its value. The call is coded in such a way that this measurement value is redirected to a file with a strange file name of $f. I will explain those dollar values in a moment. For now, $f means that after the call completes, DPS control will open that file, read the first line and insert that value into the recording file. At the moment, both the Windows and Linux scripts just echo a fixed number of 123.4 for testing purposes. The second set of calls call FFmpeg to take a picture from a webcam. In this case, you see $R and $N as file names for the image. These dollar keywords help in synchronizing the output from those commands with the running program. You don't have to use them, but they are quite useful. Don't forget that Your program may contain long ramps to test the device, and as a consequence you may do hundreds of calls. Somehow, it is necessary to make sure that the outputs of those calls don't override each other, and to mark the data in such a way that we can correlate it with what was happening in DPS control at the same time. Here's a quick overview. If the parameters in the call instruction contain a $D, it's automatically substituted by a string that contains the current date and time. As this increases all the time, it creates a unique file name with no danger of overriding an existing file. Like in the example, you can always add your own extension and a prefix if you want. $N is substituted by the call number, which increases with every call instruction. Very useful, for example, to name images. This number is also in the recording file, and therefore it is easy to find what was going on in DPS control when that image was taken. $R looks similar to $D, but the difference is that $D gives you a unique file name every time you use it, even in the same program run, and $R is unique only from one run to the next. While a program is executing, $R will always give you the same substitution, which happens to be the same as the recording file name, which makes it very easy to keep those files together. This is most useful for images. If you go back to $N, you can see that if you use $N for the image name, they will get overwritten in the next run unless you copy them somewhere else first. If you use the combination of $R and $N, as in this example down here, there is no danger of accidentally overriding the image, and all images of the same run have the same prefix, which makes finding all these files that belong together rather easy. By the way, those 4 substitutions down here do exactly the same as their non-braced version, but allow the key to be followed directly by text. Without the brace notation, the program cannot recognize the $R immediately followed by an underscore or the $N followed by a file. $F looks very similar to $R, but the substituted string is already prefixed with an underscore and ends in .tmp. The idea here is that this is a temporary file which contains a value, so after the call is completed, DPS control will read the $F file, extract that value and insert it into the recording. After that, DPS control will delete the $F file. $$ is just a method to keep the $ character in your input if that's needed. These substitutions may sound a bit daunting, but it will hopefully become clear with a real-world example. Before that, let's look briefly at the DPS control itself and how to use it. DPS control consists of the main program and 2 classes: DPS handler, which takes care of the communication to the DPS module, and DPS recorder, which does the recording. As a minimum, you need to specify a file with a program to be executed. DPS control searches for a serial port provided by the CH340G chip on the USB to serial board that comes with the DPS module, and uses that as the default for the port parameter. However, if you use Bluetooth, or if you have multiple USB to serial converter with the same chipset, or if your board happens to use a different chipset, you can of course specify the port to be used. By default, the speed is assumed to be 19,200, but you can override this with the speed parameter. The debug level is by default 1, which produces a trace of what your program is doing. I find this listing quite helpful. You can turn this off by setting the level to 0. The call for Windows or Linux is almost identical, and the same code can be used for either environment. Here is a complete program written in this language. It ramps the voltage up in 1 volt steps of 1 second duration up to 5 volts, waits a bit, does some external measurements and takes an image, and then ramps the voltage down to 0 in 0.5 volt steps. By now you should be able to make sense of the code, and it is in fact almost identical with the code shown for the goto instruction. The only different part is the setting of the protection at the beginning and the call instructions in the middle. Since they are operating system specific, you must use either the Windows or Linux version when you run this. Let's see it in action. The trace listing shows each instructions as it executes. First is the line number in your source file, then the instructions and the parameters, and in some cases additional information. For example, inc shows what the new set value is after the increment has been applied. Conditional wait and gotos show if the condition was met or not. You may wonder why the wait statements are repeated so often. This is because wait can't just sit there, it must allow the main program to continue talking with the DPS and fetch updated values to allow testing conditions. You can see that the $F and $R and $Ns are substituted in the trace as well as the values obtained from the measure script. Let's look at the files that are left after this program finishes. We have the JPEG file of the picture and the recording file. The temporary $F file has been deleted automatically. The picture shows a discrepancy of 180 millivolts between what the DPS showed and what the multimeter showed. I tested the accuracy of the DPS with this multimeter before and it was pretty much spot on. Since in this case the multimeter was connected at the load, a 20 ohm resistor by the way, that load is due to the cable resistance from the DPS to the load. It shows that even at a moderate current of just 240 milliamps, cable resistance starts to make a difference. Last not least, a quick look at the recording file using the spreadsheet program from LibreOffice in this case. We have left to right, time, the set voltage and current, the output voltage, current and power, and the voltage into the DPS. If prot shows 1, protection was triggered. CVCC of 0 means constant voltage, 1 would be constant current. Calls shows the call number and res the content of any $F file. You can easily visualize the up and down ramps by using the built-in graphing tool, which works very similar to Excel. Notice the slight lag between the blue set curve and the yellow output curve. This is caused by the delay in getting measurements back from the DPS. We can't poll faster than about every half second, so the DPS output has changed already, but it takes up to half a second before the DPS control gets its confirmation of that. Well, I admit this was a pretty dry stuff video, but I hope you agree that controlling the DPS module in that way is pretty cool. As always, the code is available on my GitHub page, links in the description below. Thanks for watching.